Welcome everybody to our CRI-O security deep dive. I'm Sascha, I'm one of the hosts today, and I'm the maintainer of CRI-O and one of the presenters today, and I'm happy to serve for you as well. And I also have Dan Walsh on my on the presentation, who is also very well known for contributions to container runtimes like CRI-O, and also some other container runtimes like Podman, Scopeo, Builder, and many more. So what are we going to talk about today? So first of all, I would like to talk a little bit about the basics of container security. So generally, we have to talk a little bit about how we want to have container security in terms of actual Kubernetes and things like that. After that, I would like to talk a little bit about how we secure container images, for example, container signing and container encryption. And after that, we can speak about actual container security features like Linux capabilities, Seccomp, SELinux, and also AppArmor. And after that, we will give a little look out into the next namespace changes in CRI-O, which are one of the upcoming topics in container runtime development. So basic container security principles. First of all, we have to choose the right amount of isolation when it comes to securing a container workload. And this can be very hard because we have to deal with different kind of layers of container security. Like we have security in runtimes like runc, and we have also security in terms for CRI-O, for example. And on top of that, we also have to speak about container security in conjunction with Kubernetes. So we have to speak about features like how to utilize Seccomp, SELinux, and even AppArmor to make our workloads more secure per default. So this basically means that container workloads have to run with the least possible privileges. But this doesn't only apply to running containers, it also applies to container images. So they have to be secured as well. The container content, for example, the default execution parameters of the container images can be reduced to reduce the actual attack surface from a container runtime. So distributing container images should also happen in a secure fashion. So we have to deal with container encryption and also container signing. But what is actually a privileged container? So I found multiple definitions across different projects like Kubernetes and Docker. So privileged containers have most of the root capabilities on the host machine. So for example, if we speak about Kubernetes, then the pod sandbox shares the network, PID, and the IPC namespaces of the host. Running privileged containers also disables features like AppArmor, Seccomp, and Linux capabilities at all. So you have to be aware that if we run containers in privileged mode, then we can't use features like AppArmor or Seccomp in the same manner. Privileged containers also mount critical paths into the container. For example, the host devices. And Kubernetes, for example, supports privileged containers by the pod spec. So we can specify a pod.spec and containers privilege security context, and then we can set privilege to true. If we set just one container in the overall workload to true, then the sandbox will also run in privileged mode. This is root caused because the pod spec doesn't have the privileged field in the security context at all. So what is the least privileged container we want to run? So restricting pod and container security context to a bare minimum is actually a good approach. So we don't want to share the host, PID, or IPC namespaces, which are also off by default, so we are good to go. Then we would like to run the workload as non-root user and in a non-privileged group. So this can be done by, for example, if we build the container image, then we can specify or set default users that we don't have a need to actually run the container workload as root user. We also want to drop unnecessary capabilities from the container. And in the best case, we would drop all capabilities from the workload, but that is not possible in every case. Because usually capabilities span some syscalls, which can be more fine granular adapted by, for example, like features like Seccomp. We also may want to disable the privilege escalation to forbid that higher privileges can be accessed by the parent process. This is on by default, and I can just recommend to turn it off. And then we can also apply a Seccomp profile. So most container runtimes come with a default Seccomp profile. But if we are able to actually specify a custom Seccomp profile for our workload, then we can drop even more capabilities or can also drop even more syscalls. We can also consider adding an AppArmor or SELinux profile to the actual workload. For example, this kind of overlaps with Seccomp. But if we speak about AppArmor, then we are able to limit access to different paths inside of the container as well. And on top of that, we can also enable read-only root file systems from a pod level. It's just a great security enhancement as well. All in all, I must say that reducing the attack surface of a single workload is more or less a trial and error approach. So we can not be sure in every case that the workload still works as intended if we just drop some capabilities, for example. So, but there's more than just securing the workload. So we have different Kubernetes features on top of that, which should be taken into consideration. So for example, we can use service accounts, cluster roles, or namespace roles, and cluster role bindings, or namespace role bindings to strip down the possibilities the application has per default. We also have to consider pod security policies, which should go away in future Kubernetes releases, but we don't have an adequate alternative for it. So we can consider using pod security policies, and we can also apply network policies to the whole application, which makes the application all in all more secure. Beside that, we also have some other security hardening possibilities on the node level in Kubernetes. For example, container image signing features, and like enabled image signing in CRI-O and enabled image encryption in CRI-O will reduce that possible attack surface when it comes to man-in-the-middle attacks, for example. Then the container images can be encrypted as well. And we can also limit access to etcd. For example, we can also encrypt secrets at rest level. And there are many more features which are a little bit out of scope of this talk for now. So let's focus a little bit on the CRI-O perspective, from the CRI-O container runtime perspective. So the first thing, so container images, signing and encryption in CRI-O works out of the box. We added the new configuration option, which can be specified via the decryption keys path. It's an option which defaults to etc CRI-O keys. And if we put our keys into that directory, then CRI-O supports OCI image encryption. These encrypted images are usually visible via the media type plus encrypted. Pulling signed images is also possible in CRI-O. So we have the container configuration in etc containers, and we can also enforce signing container images via policy.json. Just let me share my screen. I prepared a little demo for you. So here we go. What we see is that we have a single node Kubernetes cluster, and we have a running CRI-O on that window. This is my demo. And then we have a running Kubernetes stack. So if we run kubectl get pods, then we can see that we have just running kubedns here. So let's take a look how container image signing works. If we look into our registries directory on my local machine, then we can see that we have a default file which specifies a default SIG store for staging. So this SIG store will be used, signature storage will be used when we actually sign those images. So they will be put in there. And we also have two other files where we can specify container registries and signature storage locations which are served from an HTTPS endpoint. And for example, for registry.opensuse.org, we have specified a signature storage registry opensuse.org/sigstore. To enforce a policy like that, we can write a policy JSON file. For example, we can specify that in that JSON file where our transport Docker is specified, and then we enforce on registry.opensuse.org a GPG an encrypted key, and the key path can be distributed, for example, by the distribution itself. And in our case, it's the public key from registry.opensuse.org. And yeah, if we now pull a container image from registry.opensuse.org, then we can have a look if should succeed at all in a couple of seconds. And we can also have a look into the CRI-O logs. And for example, here we can see that CRI-O automatically tries to access the signature storage and also automatically downloads the signatures for the container images layer. And this usually works in a couple of seconds. And now we are done. We downloaded the image. And yeah, if we, for example, now consider removing that image again, and yeah, just for demonstration purposes, we move the GPG key to a different location. And then we try to pull the container image again. Then it should fail because the policy.json would like to enforce the... I copied it. 1 second. I have to move it. That's not correct. Otherwise, the file wouldn't move. So if we go into etc containers GPG, then we can see that we just have it as a backup image. Let me just remove the image again. And then we pull it. Then we usually should get an error. Hopefully this works. Yes. All right. So now we get an error message that none of the signatures were accepted. So the GPG keys doesn't work at all because it's not existing. But even if the GPG key is not valid or not valid for our signed image, then we would get a different or a similar error message that it's not possible to download the image at all. Now let me just move it. I can do it later on. So then let's talk a little bit about running secure workloads with CRI-O and Seccomp. So Seccomp graduated to general availability in Kubernetes 1.19, which should be released in the next couple of days if we speak about KubeCon Europe. And previously, this would be handled via pod annotations. And from 1.19 on, we have a dedicated field on the pod security context or on the security context on the container level. This means that we have now a security context, then Seccomp profile, then we can specify a type like runtime default or localhost or unconfined. And if we specify localhost, then we can also set the localhost profile to a local profile. So those local profiles will be looked up into the kubelet directory, which should be usually warlib kubelet. It's the kubelet root, and then /seccomp. So if we put the profile into that directory, then we can usually reference them directly via myprofilename.json. I can demo that for you as well. And we are now on the same cluster. So as already shown, let's just have a look at our Seccomp example 1. So what we have here, we have a deployment, Nginx deployment. Then we specify our security context and our Seccomp profile, in our case, runtime default. So CRI-O ships a default Seccomp profile, which is included in the CRI-O binary, but also with some distributions distributed via a file called an etc containers Seccomp JSON. So this is a pretty good Seccomp profile, but you can see, for example, we have some syscalls which are allowed by default. And not every application may need all those syscalls to be executed in a normal way. But let's try it out. Let's create our Nginx deployment. And the containers are now in container creating state. And now they are running. And if we run cryctlps to get an idea about which containers are running, so we have both here. And if we run cryctl inspect and then specify the container ID, then we can see that then we have a reference to the whole Seccomp profile directly in the inspect, because usually the container runtime, like container runtimes like CRI-O, pass down the Seccomp profile to the underlying container runtime, which is runc in that case, and then runc applies the Seccomp profile. So that's this one. So this works pretty cool. Let's just delete our deployment again, because usually we can't change the Seccomp profile on the fly, so we would have to recreate the workload. And if we now look into our second example, then I just did more or less the same, but now we add the security context to our container. So we specify now a Seccomp profile from localhost path, and we choose our demo.json. Our demo.json is located in warlib kubelet seccomp demo.json, and it's basically the same as the default profile, but it just forbids rmdir. So rmdir is just a syscall to remove a directory, so it shouldn't be harmful for our nginx application. But let's just try it out. We just recreate the workload, wait for the containers to be created. And yeah, then let's just exec into one of our nginx pods. And here we are. And now, yeah, I'm root user inside this container, but I usually should be able to, for example, create a directory test, but shouldn't be able to remove the directory again. Yeah. And now it says that the operation is not permitted because the Seccomp profile enforces that. And yeah, if we speak about Seccomp at all, then it's not that easy to write those profiles by hand. But there's a little nice fancy project called the OCI Seccomp BPF hook, which can be used, or which is just the general OCI hook, which is supported by CRI-O at all. And this OCI hook can be used to trace syscalls and generate Seccomp profiles out of the box. So I can really recommend to play around with it. And it works also very well with Podman. And for example, if you run it with Podman, then you can specify the annotation io.containers.trace syscall, and then some input. It's not necessary to specify input path, but it's necessary to specify an output path, and then you will get the Seccomp profile generated into that path. So what other options do we have to actually secure our workloads? So the next thing I would like to talk to you about is AppArmor. So AppArmor is still a beta feature in Kubernetes, but we also try to consider to move it to GA very soon, maybe in 120 or 121. And right now we have to handle it via pod annotations. So we have to specify an annotation at the pod level, which is called container.apparmor.security.beta.kubernetes.io. And then we have to reference a container name and the profile ref. And this profile ref can be runtime default. It can be also localhost/profile name, like we do in Seccomp. And then we can also set it to unconfined, which disables the feature at all. So I just would like to give you a short demo about that as well, because I'm running on a system which supports AppArmor. And let me just delete my Seccomp workload. And AppArmor works a little bit different than Seccomp. So AppArmor profiles are usually stored in memory. And I created a profile called container nginx in etc AppArmor-D, and every profile in etc AppArmor-D will be automatically loaded if I boot up the system, because AppArmor stores automatically. So this profile looks like this. We don't only can limit network restrictions to the actual workload. We can also specify root level permissions, and can also for example, drop capabilities down here. So we have a lot of flexibility in that profile, but it follows a dedicated syntax. So we also have to test it or create it manually. There's also something like an AppArmor recorder, but I don't want to talk about this at that point. So this profile seems pretty well. now let's just check if AppArmor is running. So we can run AA status, and then we look for Nginx, and then we can see that our Nginx profile is successfully loaded. So if we now look at our AppArmor demo example, then we can see that we have the annotation here. We specify container AppArmor security, and our container is named Nginx-CTR, and that's the container down here. And we use the localhost Nginx profile. So let me now apply that profile, that workload, sorry. And if now we can see that it's running again. Let me just check the containers running, and if we inspect that container, then we can see that the AppArmor profile Nginx has been loaded successfully. So this is pretty nice. And usually we can also go into let's just exec into our Nginx container again. And if we take another look at the profile, then we can see that we can't access /bin. Yeah, so I'm just root in that container. So I usually have root level access. I can create directories like test, but I can't go into bin and create their directories like test. Yeah, and it says permission denied. And usually the audit log does give us an indicator. Audit log gives us an indicator about what actually happened on the system, and we can there we can see, for example, there's an audit log for Nginx, and we tried to create our root level directory test, and this actually works. All right. So that's it from my demo for AppArmor. And now I would like to hand over to Dan, who speaks about capabilities.
Okay, great job, Sascha. So basically this part of the talk, I'm just, as Sascha in the beginning of the talk talked about, we really recommend that everybody run containers without being root inside of the containers. And, for the most part, I believe that almost all workloads should be able to run without being root, and that's probably the most secure way you're able to run it. But in certain workloads, people need to be run as root, or need to have multiple UIDs inside of a container, and need some of the root capabilities. So the idea of Linux capabilities is it divided the power of root. So sort of everybody understood root as being all powerful. And many, many years ago, the Linux root capabilities, Linux kernel basically broke down root into a whole series of different capabilities. So the interesting thing about containers, and this was sort of developed by Docker a long time ago, is they figured out that you could run almost all workloads by default with just a small group of the capabilities. So the power of root was broken into 37 different capabilities, but actually Docker sort of standardized on 14 capabilities that it ran for containers. And we sort of latched into that, and most container engines now have settled on those 14 capabilities. The problem with those 14 capabilities is nobody knows what they are, right? So it's sort of, even I, who deal with this a lot, I couldn't probably answer a test and get all 14 right. What I have done is I've actually looked, and so here are the 14 capabilities that are allowed by default in most container engines. But when I sit down and look at these, I look, what is the history of some of these? Why are these on? So, for instance, this one is audit write, and audit write is the ability to write to the auditing subsystem. So Sascha showed you, looking at AppArmor errors in an audit log. So the audit write allows you to modify parts of the auditing system to be able to manipulate the auditing system. So why would we have that on by default in containers? And it turns out that when containers were first becoming popular, most people thought of them as as virtual machines. And what they wanted to do is they wanted to run SSH daemon inside of them. But when they launch a container with SSH daemon running inside of it, it would blow up, because the SSH daemon, when someone tried to log into a system, would basically write a record that said Dan Walsh logged into the system. And that would be blocked because it didn't have audit right. So that got turned on by default for all containers. And of course, almost nobody runs SSH daemon inside of containers now, but we still have that on by default. The next one I want to look at is make node. So make node is a capability that allows you to create device nodes inside of containers. But again, when we look at CRI-O and Kubernetes, we're looking at running containers in production, and you really don't want to allow containers to create random device nodes. What we want is the container engine to create the device nodes and not allow them to just create random device nodes on their own. But we allow this by default, and the reason we did that is because originally people were doing lots of installs and builds, and certain packages, I believe from Ubuntu, actually created device nodes during the installation procedure. And so really, when we're running containers in production, we're not building container images, and we're not installing RPMs. So why do we need make node on by default? The next one I want to talk about is netraw. And netraw is a capability that allows you to create any type of IP packet. So TCP, ICMP, any type of IP packet can be created and then put out on the VPN. And the problem with this is it really gives an incredible amount of power and has led to some escapes where people were able to break out of the virtual private network by forming packets in a certain way. And the real reason for netraw being on by default is that so people could actually execute the ping command. So when I execute a ping command, I create an ICMP packet and put it over. So when I went into a container, I'd want to create that. So again, it's an incredibly powerful capability that really we don't need on by default, especially for containers in production. And the Linux kernel has other ways of running allowing you to create ICMP packets so you can continue to ping. So we actually, enable that by default in CRI-O instead of netraw. And then the last one is syschroot. And syschroot is a capability that allows you to create a chroot inside of a container. But a container is really kind of a super powerful chroot. So why, most people aren't creating chroots inside of containers. So why do we allow that by default? So when in CRI-O, what we've done is we've looked at this original list and we basically said, let's get rid of some of these ones that are less necessary. And we're able to run almost all of our containers without these 4 capabilities. So we can drop down to, just basically 9 or 10 capabilities that we run by default for our containers when you're running as root. The next thing, and obviously, in capabilities are fully available inside of Kubernetes. So if you do find a container that needs additional capabilities or something that's not allowed by default, then you can add those capabilities through your Kubernetes YAML file. So we can override those if you need them, but really, at base level, we want to run everything as tightly as possible from a container point of view. The next thing I'm going to talk about is SELinux. And SELinux and AppArmor are 2 ways of doing what's called mandatory access control or control on systems. One difference between the way SELinux works and the way AppArmor works is that AppArmor is controlling mainly what's going on inside of the container. And what SELinux does is it wraps the external part of the container. But the really great thing about SELinux is that just about every type of file system breakout, when the process is able to break out of the container and get to the host or attack other containers, has been blocked by SELinux out of the box. So quickly, people tend not to really understand what SELinux is. And a few years ago, I wrote a coloring book on that, and I'll just go through it real quick and try to sort of explain what's going on with SELinux. And think of every SELinux is a labeling system. Everything on the system has a label. So let's say there was a cat process and a dog process, and so we have a process type, a type of a cat and a type of a dog. And then I have food. So every object, every directory, file, system, everything on the system is labeled with a label, and basically we have a label as cat food and we label one as dog food, and then we write rules into the Linux kernel that basically says allow a cat process to eat cat food and allow a dog process to eat dog food, and the basic idea here is that everything that isn't allowed is denied, and this is really exactly what an SELinux rule looks like when written to the container. So now if the cat tries to eat the cat food, it's allowed to eat, and if the dog tries to eat the dog food, it's allowed to eat that, but when the dog tries to eat the cat food, it's blocked. So from a container point of view, this means that when I'm inside of my container, I can do, we basically launch the process as being a container type, and then we launch the content inside of the container as being container files, and we write a rule that says a container can read and write container files. If the container process broke out and tried to read the home directory or try to read any other directory on the system, and that content isn't labeled as container content or container files, then it will be blocked by default. And that's how SELinux is blocking all of the potential escapes or file system escapes and containers. So those are sort of the hard-coded built-in tools that we talked about, Seccomp capabilities, SELinux and AppArmor, and some of the other features that Sascha talked about. One of the things we're really trying to finally accomplish is actually to get user namespace. So I mentioned earlier that people want to be able to run root inside of a container, or they want to be able to run multiple UIDs inside of a container. And so we have a pull request right now into CRI-O that hopefully will get merged soon and will become a feature to allow you to specify an attribute that allows you to basically enable user namespace. So what happens if you need root inside of a container? And what happens if you need more than one UID? And some use cases where this becomes important is things like building container images. So most people that do builds inside of Kubernetes right now need to have root or need to have multiple UIDs inside of the container. So they end up having to run privileged containers, or they end up having to do things like leak the Docker socket or some other container engine socket in and basically break out of confinement. Another thing would be, they're needing to launch multiple processes inside of the same UID. So by enabling user namespace allows us to map root and other UIDs inside of a container as non-root on the host. And what we've done in CRI-O now with the latest pull request is to allow us to basically run different containers, different workloads that require root or multiple UIDs to be able to run as root inside of the container, but if they break out, they're treated as like non-root on the rest of the system. And we've enabled that from the top, from the highest level, in CRI-O all the way down through container storage, and we're handling some of the relabels and images. So this is a really cool feature that's going to be coming very soon to CRI-O systems. So at this point, we're racing to get this talk done, and at this point, we could open up for any questions.
Hello, everybody. So here we are live and in color. First of all, I would like to apologize for not uploading the slides to SCED, but I did share the link in the Slack channel and you can access them via that. Okay, then we have a couple of questions left.
So one of the questions earlier was basically talking about an exploit allowed because of cap make node. And I, as I said in the talk, cap make node should really be turned off by default. There's almost no reason for that to be on. And if you need additional capabilities for your containers, then you can specify that in the Kubernetes YAML file. Another question about what is the relationship between CRI-O and Podman. So Podman is a container engine for running sort of traditional, what people think of as the Docker workloads. CRI-O is basically a daemon process for running Kubernetes workloads. They both share the underlying mechanisms for pulling images and storing images. So they share a lot in common, but they both can run totally independent of each other. So the question on there's a question on SELinux. Is there a new SELinux syntax for SELinux configuration to distinguish between in-container object processes and things outside of the container? So from an SELinux point of view, we'd like to run all of the contents inside of the container as a single label. We believe that this is the way microservices should be written. So we treat all content inside the container as one label, and then if they break out, they're treated as a container, and therefore they're only allowed to read and write container content. Each container has a separate, what we call MCS label, but basically it's a unique identifier for specific containers. But right now we don't support multiple labels inside of containers. This is one big difference between AppArmor and SELinux, and AppArmor is actually providing security or separation inside of the container, whereas SELinux is providing separation outside of the container. So they work a little bit differently in that case.
One question is, what is the relationship between Docker and CRI-O? So does it work as the same as it does in Podman? Yeah, CRI-O and Podman share common source code and dedicated libraries. So all security patterns which apply to Podman should also apply to CRI-O. And there is not that big relationship to Docker anymore. But for example, if we look at a default Seccomp profile, then we can just say that historically it has been inherited by Docker. Yes, that's some historical relationship.
Yeah, the main comparison between Docker and CRI-O is around container images. So CRI-O and Docker both support what's called OCI images. And so at the input, so anything that exists at any container registry, Docker.io, Quay.io, Artifactory is supported because there's a standard around what a container image is. And also the way we launch containers, we also use a standard called the OCI Runtime specification. And we're both using right now Runc for launching containers. So the containers on the input and the containers on, when you execute them are both run the same exact way between Docker and CRI-O. So therefore they can support all of the same content and Podman as well. We've just been notified that we're running out of time now. We will be available on the Slack channel to answer any other questions that people have, or if we didn't get to a question here, just ask it on the Slack channel. So thanks for listening, and goodbye.
Happy to see you there.